Going to show some link, right? So this link is basically a simulator. I'll share you the link. Actually, this playground tensorflow.org. I'll share with you. So what this is simple website, and what we are going to discuss today is what we have discussed last 3 days and how it is implemented. So it looks very complicated. So you just don't mind these things. So just I'll reduce it to very simple thing. And these are different layers of neurons, right? So different layers of neurons. So I'm reducing the layers and I'm hidden layers. Hidden layers is those processing layers. So I'm also reducing the hidden layers to one. Right now it is simple. Now input also I'm reducing. Now I have simple two input. You can see here two input. One neuron is the in the middle. Maybe I can zoom it. Right now I think it is clear for you. So what I have, this is the input. X1, X2 is the input, right? And you have one neuron. You have one neuron here, and this is output. This is output. So why this output is like this? Because the data input is like this. I have selected that data. You can see the left. There's a data selecting option, and I have selected a very complicated data set. It's not easily actually. It is not able to classify using usual simple neural network. So I'll just take a simple data set. There are other data set like this. This is another data set. This is less complex than the previous one, because still it is a curve. There's a curve here. And this is another data set. This is not as complicated, but still it is not linearly separable. This is the most simplest data set, right? So using one neuron, we know that we can easily draw a straight line, because the equation we have discussed is W1 into P1 weight into input 1 plus, that is here it is x1 x2, w1 into x1 plus w2 into x2 plus a constant p equal to 0. So here one neuron is sufficient, right? I can increase the number of neurons by clicking here. I'm increasing the hidden layer. This is the hidden layers. So I can go on increasing the hidden layers. You can see things are very complicated. So I'm reducing to one neuron right now, one hidden layer. Now I can increase the neuron by clicking plus here. This is the number of neurons. Okay, so uh, hello. Can I call? Can I call you sometime? I'm in class. I'm in class. Okay. Thank you. Okay. So we can select these things option. So this the epochs means they can say the simulations or number of iterations kind of thing representation. So we have different data set and we can select the training and testing data. You can see I'm changing something. What is this? This is the ratio of testing data, test data. So now the test data is only test 10%. Okay, ratio of training to test data. So what is the meaning of this? Usually we keep at 50%, or maybe, because at least 50% data is used for training and next 50% I'm using for testing. Okay, so we have 100 data points. That means 50 I'm using for training and another 50 I'm for testing. Usually we keep it this around of 60 or 80, right? Usually 60 is okay, good, and more than 60 is also 70. So 70% data I'm using for training and 30% data I'm using for testing. That's also fine. Anything more than 50% is fine. Here I'm not using any noise here. If I add noise, it becomes very difficult for the neural network. So let's put noise 0 here. And batch size, I think batch size is like at a one time, I'll be having a feedback because error will be accumulated. So if each data point, I'm calculating the error, I'm changing the weights or adjusting the weight, that means the batch size is 1. So if I take 10 batches of data, 10 individual data points, then I train my neural network. Again, I adjust the weights based on those 10 batch sizes 10. Okay, so that this will do in neural Python or MATLAB. So this is just a interface which you can play with. So here, what I'm taking is simple data. This is my simple data, and I'm using two inputs, x1 and x2. And this time I'm using only one neuron, because I know that one neuron can separate this kind of data using a straight line. Okay, now let me start my simulation. This is the top left. You can see arrow. I can start the simulation. Let's start the simulation. You can see how it is training. You can see the starting, how this simulation started. The neurons are working. You can see the straight line separation between these two data sets. Right now, the epochs are going on, iterations are going. You can see top or mid right output. This is your output. So output, it is showing there's no error. Initially, maybe you may be getting some error. For example, I'll just stop the iteration. You can start starting from scratch. Now you can see the output, test loss, training loss, something. You can just see that graph. You don't see any graph there because it's already trained. So let me change the data set or something. So let me take some complicated data. So right now, I'll change this data into complicated data. Now let me try to classify using the one neuron. I think it's not possible to do using one neuron. You can see test loss is heavy, training loss is also very heavy. You can see this not able to classify. The output is not, output is not right because it is not able to classify properly using one neuron. Right? So this is one example. Even no other cases, even these are more complicated data sets, definitely will not be able to classify these things because only one neuron. You can see the test loss and training loss as considerable. Right? This is the most toughest data set. You can see how it is. You need a lot of neurons and input neurons and layers also to classify this. Let's see, is it possible? Now this kind of input is can be classified using a single neuron. We can see the testing loss and training loss graph going to. So this is perfectly classified. Now let's change the input. Now let's take this complicated input. So this complicated input cannot be done using one neuron. So we need to increase the number of neurons. So I use two neurons. Let's see whether it is possible using two neurons. Yeah, it is not perfect. Definitely, it is not perfect. You can see still it is better than the one neuron. At least it is showing two classes, but there is some noises. One blue class on the edges and middle portion. I have a yellow class. So still it is going, and you can see the testing output, test loss and training loss is considerably comparable. All the slight error is still there because a lot of error is there because some blue points are classified as the yellow region. Right now, what I'll do, I'll change the number of inputs. Right now, you can see hidden layer is one only, but I'm increasing the number of neurons. Let's see whether this is possible. Now it is better. You can see how it is better classification. You can see the curve. The curve is much better. Still, there is some error. You can see there is some error. You can see the output graph on the top right. There's some difference between test loss and training loss. Error is the. You can see some yellow points in the blue region, some blue points in the yellow region still. So it's not perfect. So I just stop it and increase the number of neurons again. Let's see what happens. Okay. Um, right now it's also not much difference. Still the error is the some yellow point in the blue region, but it is better rather than a last time. It is now there is only one error here. You can see one yellow point in the blue region. That is the only error here. Now it is much better actually. You can see if you quantitatively note the test loss and training loss, you may be able to get a better quantitative picture also. Again, stop it and increase the number of neurons again. Again, let's see. Okay. Yeah, now you can see it's much better. You can see now that yellow point is also better, rightly classified. Right. So this is you can see the graph also there is no error right now. Difference between training and testing. Right. So this is so we can say 5 neuron input is ideal in this kind of data sets. So seeing your data set, you should understand what kind of how many neurons should I use. Right now it was somewhat linear the output, so I don't thought of increasing layers, just increasing number of neurons in one layer only. I'm able to classify nicely. Right. Okay, now let's change. Take a more complicated input. For example, this is more complicated. Let me try using this 5 neurons. Let's see. Yeah, it's perfectly classified. You can see because this is you can see middle portion is one group, outer portion another group. So this is possible using 5 neurons easily. Maybe using one less neuron, is it possible now? Sorry, one hidden layer and four neurons. Let me try. Is it possible using? Yeah, not perfect, but still it is possible using 4 neurons also. Let's see whether it is possible using 3 neurons. Yeah, 3 neurons is okay. It's fine. It's able to do it using, but two I don't. I doubt it is possible using 2 neurons. Let's see. Yeah, you can see it's not possible using 2 neurons. Right? You can see this is still there is a lot of misclassification. A lot of yellow points are in blue again. and some blue points are in yellow region. So it's not perfectly able to classify here, right? So leave it. So as we reduce number of neurons in one layer, the capacity of your neural network is very limited. Okay, now let's take the complicated thing. Now this is a very complicated data set. You can see it's like curve. It's not a straight line. It is not multi-plane. So it's very difficult. I don't think either this is possible using six. I'm using six neurons in the one layer. And let me try to classify this. You can see the error is still there. The graph, output graph, you can see there's a lot of different. Still, you can see this no no explanation that this is possible. You can see it is very complicated. You can see graph, error graph going up and down without any. So you can see, although it's trying to classify, but it's not possible. You can see even though I'm using seven neurons, so that means it's not possible. Okay, so let me stop this. This is not much effective, but still it is okay. It is trying its best, but still there are a lot of yellow points in the blue region, a lot of blue points in the yellow region. So here I have to use multi-dimension. There is more layers. Now I'm increasing layers. So I increase one more layer here with two neurons, and maybe I'll increase neurons to more, or I'll use three layers so that I have more options, something like this. Now let me try that. This is able to classify. Here also I can see I don't see the error is reducing, but yeah, now it is improving, but not perfect. It is trying its best, but still there is some problem happening. You can see the graph in the top. There is some kind of noise kind of symptoms rising. Well, I don't know what the term used for this. Maybe overfitting. I don't know what is this. Let's discuss later. But you can see there is some kind of issue happening, some kind of unstable output I'm getting. You can see the neuron. You can see this initial first layer. You can see straight lines. All neurons, you can see there are only straight lines classification. You can see straight line, straight line, straight line. But in second layer, you just see patterns are emerging. Combination of multiple lines are coming in second layer. You can see curves are in second layer, and third layer, more complicated picture is in third layer. So these are the features which these neurons are looking for after training. So we are using a very kind of very good processor. Some kind of processing they are using this website. It's in TensorFlow, I think, and they are doing in background a lot of heavy processing. So you can see the patterns in these neurons which they are trying to figure out. So anyway, we are having a failure here. So let me increase the number of neurons. In the output also, I'm increasing number of neurons. Let's see whether this will help or not. And start the simulation. So things are not easy. It is taking a lot of time. Still, the can see graph. The graph is trying to reduce the error. Training and testing is still not perfectly coordinated. Now, some kind of instability is starting to come in the uh, output, like previous case. So this means that even increasing layer three layers is not sufficient for this kind of complicated data. So what I know, we have given some more output possibilities. There is some more possibilities they have given. X1 square, X2 square. The more input also will help us. So here is a failure. We are not able to classify this data. So what I'll do, I'll try to increase the input. Now I'm going to stop the simulation because it's not perfect. Output is not classified. Now increasing the input. I'm just increasing the input. X1 square, X2 square also I'm increasing. X1, X2 I'm giving maximum input to this neural network. Why? Because I just although I'm using three layers, maybe four neural networks. So this much. Now what I'm doing, I'm increasing the number of inputs also. Not only x1 x2 is going to the input, I'm also giving them or giving the network x1 square, x2 square, x1 into x2, x sin x1 sin x2 also. So the more input it gives, the more better training, the more features it can understand. You can see the neurons what is written. X1 is only linear, x2 is linear, x1 it is some kind of pattern, interesting pattern. X2 square is also pattern, x1 x2 is another pattern. So the more pattern it is going to experience, the more better training I'm going to. Let's start with this running. I'm just going to run this. Let's see how it is going to work. Now you can see how fast it is coming to the solution. You can see all this All these blue points are blue and yellow points are in yellow immediately within so less time. Now you can see this is somewhat perfectly classified. You can see all the yellow points are in yellow and blue points are in blue, right? So this is somewhat very good because we have increased number of input and neurons also 644. That means it is a good classification, right? So it is able to predict the pattern. You can see it is how it is yellow and blue color is organized in the output. Very nicely organized, right? Now this much about this. The more complicated input, we need more inputs and more layers of neuron, more number of neurons per layer, etc. Okay, so although I'm not changing batch size, let it be the noise. I'm not adding any noise because already input is challenging. um, Fine, let me stop the simulation now. Another input thing, another important thing you can see here is there are two options. Top right, you can see classification and regression. So what is classification? We are doing classification. Regression means you can say prediction. I'm giving a lot of data and I'm telling the neural network to predict. Although I'm not gone through the regression part in this model, so I don't want to explore wasting your time. So another option here is TANH, activation function. You can see there are different options of activation function which the user can select. One is TANH. We are using TANH. Although there was no reason for me to use TANH because it was already by default TANH. So let's see what is TANH, how the TANH looks like, activation function. So this is TANH activation function. So you can see this is the activation function. Over zero input, I'll get zero, and all my values greater than zero, or all the positive numbers are mapped into values between zeros and one in the y-axis, right? So this is also a good kind of mapping. All the real values are mapped to values between 0 and 1, the positive direction. If the values is negative, it is mapped to 0 and minus 1. So this is a good activation function, right? Now, what are the other options I have? Here you can see the other options other than TANH. I have sigmoid. Actually, sigmoid we had discussed yesterday. So let's run it sigmoid. Parallelly, we'll check what is sigmoid. Sigmoid. This is sigmoid activation function which we discussed. Yeah, this is sigmoid activation function. You can see this is unlike TANH, it is more reaching high, one value much easier, much easily than TANH. TANH will take 0 to 90, 45 degree, all those things, a lot of time. But you can see sigmoid is much better. This we have discussed. But you can see this is a 0. If the input is 0, it is mapped to 0.5. And all the negative input is mapped to values between 0.5 and 0. And all this value greater than minus or less than minus 0.4 is already almost 0. And all the points greater than 4, positive 4 is almost 1. Right? So this is a sigmoid activation function. So let's see what is it is doing. Yeah, it is not. I don't think. I don't know whether it is able to do it or not. Yeah, definitely it should be able to do because we have a lot of inputs, a lot of neurons we invested. Maybe it takes time. Yeah, this coming. Yeah, it's doing better. You can see right now it is done it. You can see the training and custom. Okay, now other option of activation function is ReLU. ReLU. I just show you ReLU activation function. This is ReLU. This is you can see here all these values less than 0 is mapped to 0, and all the values positive values is linearly. Uh, okay, you can say it is. There was a linear activation function, right? Real linear activation function. So really is a like linear, but you can see the difference between linear is always linear. That means 0 is mapped to 0, 1 is mapped to 1, minus 2 is mapped to minus 2. So like this is x equal to y graph kind of thing. This is linear activity. Although in neural network there is no point of using linear activation function because already I don't think we have using linear. So real linear. So ReLU means some kind of linear, but I'm putting the negative all to 0. So that is ReLU. Same thing, but negative values are always 0. Negative values we are mapped to 0, and all the values positive values are mapped to similar values. So I'm just cutting out the negative. So the ReLU is used in those applications where I don't need a output is negative. I can use a positive output using ReLU. Okay, so this one now you can see is perfectly classified. can stop the epoch, right? And so there's a learning rate. These all things we'll discuss while we discuss the equations of feedback and all those things. So this is just a and regularization we'll not discuss right now. L1, L2 regularization. Again, rate is also there, so we don't need to discuss all those things. So at least I'll share the link, and that's much for this. So whatever we discussed last few classes, we were just to get a feel of those things. Okay. So I also shared some JavaScript also, which you can play in your um, computer and get the same feel. You can also see the straight line changing in that. Okay. I think if any quick questions, I will be able to take some quick questions. So let me stop recording.